Let us proceed with module 5. In this module, we are pending with semiconductors and dielectrics. So first let us see the semiconductor in this part 5, wherein we will initially study the introduction to energy band gaps and then classification of semiconductors, that is N and P type, and doping, and due to doping it is N and P type semiconductors are there. Then we look into the energy band gap, and then we learn what is a Fermi level. Just to recap, in the previous classes we have studied with the classical and quantum free electron theory, some definitions in both the cases, and merits and demerits in both the cases. In the remaining part, we need to study the physics of semiconductors and dielectric materials. In semiconductors, we need to just learn about the Fermi level in intrinsic semiconductors and expression for concentration of electrons in the conduction band, and whole concentration and conductivity of semiconductors. A small derivation is there. We need to learn about Hall effect, and also we need to derive the expression for Hall coefficient. In the case of dielectric materials, we need to learn about the types or polar and non-polar dielectrics, internal fields in a solid, and we may have a small derivation of Clausius-Moussetti equation, and we need to know about solid, liquid, and gaseous dielectrics with the examples, and also the applications of dielectrics in the transformers. Before going further, let us just look into the origin of band gap. So wherein we have, you might have remembered in the previous classes of quantum free electron theory. So these are the bands, they have filled bands, wherein you could see this is in the case of sodium. So wherein you could see that 1s, 2s, 2p, and 3s are filled. 3s is of course half filled, and 3p is not filled. So not filled means it is a vacant, and here it is a filled one. Okay, and then the gap we call it as a energy band gap, that is in any solid. So the origin of energy band gap, which if we just generalize, then we can write it as the conduction band on the upper side and valence band on the lower side. Okay, and the gap between them we call it as energy band gap. The energy band is filled to its maximum capacity, then it is said to be a filled band. In an energy band diagram, there will be a band called valence band, which below which all the bands are occupied, and above which all the bands are empty. So empty band, which is immediately above the valence band, is called conduction band. The gap between them we call it as a forbidden bands, or energy band gap, represented as Eg. So this energy band gap, which helps us to classify the materials into good conductors, bad conductors, and semiconductors. As you could see in the figure here, the first one is referred to the conductors. Conductor means wherein you see that the energy band gap is overlapped. Okay, in the case of semiconductors, there is a small gap here between a valence band and a conduction band. That gap is around 1.1 to 0.7 eV, electron volt. And in the case of insulators, you have very large energy band gap, so which we call as a forbidden energy band gap. Okay, in such cases, electrons jumping from are very difficult, and we call them as insulators. Okay, as we have seen earlier, materials can also be differentiated into conductors, semiconductors, and insulator based on the conductivity. Okay, this slide also we have seen. Let us see the example here. Silicon, germanium are the elemental semiconductors, and PVT, CDS, that is cadmium sulfide or indium antimony or gallium arsenide or gallium phosphate, etc., are called the compound semiconductors. In the case of semiconductors, they are broadly divided into intrinsic and extrinsic semiconductors. Intrinsic semiconductors are the pure semiconductors, but in the case of external, they have some tertiary element inclusions. Okay, and extrinsic semiconductors are again divided into two types based on the impurities. So they are P-type and N-type semiconductors. So intrinsic semiconductors are highly pure elemental semiconductors. Their conductivity is slightly less than that of the insulator. For example, elemental silicon and germanium. And at absolute temperature, absolute 0 degree centigrade, 0 degree Kelvin, they are insulators. Above absolute temperature, at 0 temperature, there is a finite probability that an electron in the lattice will be knocked loose from the position, leaving behind an electron deficiency, which we call as a hole. In other words, as the temperature increases, electrons are thermally excited from the valence band to conduction band, and both the electrons in conduction band and the holes in the valence band will contribute to electrical conductivity. In the case of intrinsic semiconductors, the concentration of hole is equal to the concentration of electrons. That is why Ne is equal to Nh. That is why sometimes we just represent it as Ni, which is nothing but intrinsic charge carriers per unit volume. Current which will flow in an intrinsic semiconductor consists of both electrons and hole. Fermi level in the intrinsic semiconductor lies in the middle of forbidden band gap. Next, let us go for extrinsic semiconductors. So these are the semiconductors with the external elements, and it is an intentional addition. The process we call it as a doping. The process is called as doping. Now look at this periodic table, wherein I have just marked here near the semiconductor silicon and germanium. You could see the outer boundary here, which consists of some elements, and it is simply, if you could understand the periodic table, you will understand the type of doping. First, let us see what is doping. Okay, doping is a process of deliberate and controlled addition of an element to the semiconductor to tune its conductivity. Means we can change the conductivity of the material by adding additional element or any other elements. For example, you see the increase in the resistivity. If one boron atom to 10 to the power 5 silicon atoms increases the conductivity of pure silicon by a factor 10 to the power 3, means almost 1000 times at room temperature. To explain doping, I have taken the extract of periodic table here. You could see, you can refer the periodic table in the few slides before. So wherein now let us explain doping, and we are going to produce a p-type semiconductors. Okay, let us just consider silicon here, and you know the silicon electronic configuration. Its atomic number is 14, so 3s2 3p2 is there, so we call this as a tetravalent. And for this we are going to add boron. Okay, boron means it is a trivalent, which is on the left hand side of the group in the for a silicon. Okay, so because in boron we are having the final configuration, electronic configuration, as a 2s2 and 2p1. Okay, so in this 2p1 means we are going to have one electron that is going to be there, and by adding boron, 3 valence electrons will combine with 4 valence electrons of silicon. Okay, so 3 whatever is present here is going to combine with 4 electrons that is present in the silicon. Okay, so one more electron is needed to have a complete tetrahedral covalent bonding. Okay, so that needed means there is a vacancy. So that vacancy is nothing but the hole. We call that as a hole. Okay, so we are creating the holes by adding boron, or by adding the atoms which are present in trivalent, like boron, aluminium, gallium, and indium, etc., and which are also called as acceptors. And the resulting semiconductor, we call it as p-type semiconductor. Similarly, we can explain the creation of n-type semiconductors. Here also let us consider silicon to start with as a semiconductor element, and we add the pentavalent elements. Okay, so for example, let us add arsenic here. For arsenic, as you could see, the electronic configuration for 33 atomic number is finally it is 4s2, 3d10, and 4p3. Okay, so this is called as pentavalent. Okay, so that means there are 2 plus 3 here. Okay, 3 electrons there. Okay, so as we know, silicon needs exactly 4 electrons now to complete the orbital. So by having the 5 valence electrons of arsenic, which will combine with the valence electrons of silicon. So we are having one excess of electron. Okay, so by adding arsenic, we are having excess. In the previous one, in the trivalent, we are having a deficiency of electron. Now we are having excess of electron. So this excess of electron will be as a free electron for conduction, available for conduction. Okay, so by adding pentavalent elements such as this phosphorus, arsenic, antimony, or bismuth, we are going to have electrons, extra electrons. So that means electrons are available for conductions. So that means those elements are called as donors. Okay, and the resulting semiconductor, we call it as n-type semiconductor. This slide presents a picture of the previous explanation. So wherein for this is for n-type, as you could see, it is arsenic that has been doped. Arsenic is the impurity that is doped, and there is an excess electron, as you could see here. Okay, so this is how it is n-type of semiconductor is produced. In the case of p-type semiconductors, as we explained there, it is we had explained as a boron, and we are having a vacancy here. You see, electrons are present here, it is present here, it is present here, because it is a tetravalent. So because boron, we are having a vacancy. So this vacancy we call it as a void maybe. So that is what is a hole and the creation of p-type semiconductors. Here is a list of few of energy band gaps. So first you could see here these two are the elemental semiconductors. You are aware that its energy gap of silicon is 1.1, and energy band gap of germanium we can take it roughly 0.7. And you could see for insulator energy band gap is 6, that is for a diamond, and for a tin is a metal in fact, and is or a semi metal which has a energy band gap of 0.08. Okay, and in the case of lead is a metal itself, so lead wherein you have a forbidden energy band gap, you don't have a energy band gap. Okay, and okay, there are some elemental compound semiconductors like aluminum antimony, or gallium phosphate, or cadmium sulfate, cadmium silicate, celerium, or zinc tellurium. So these are some of the semiconductors that we have. I'm giving here one of the interesting applications of studying the energy band gap. Why we need to study the energy band gap? For example, in the case of solar photovoltaic cell, we know that sun's energy is being converted into electrical power. Okay, so sun energy, that is in the visible range, right? So that means in the visible range we are having the frequency and wavelength in this order. Okay, for that the corresponding quantum energy is 1.6 to 3.1 EV. Okay, so this is what we have, and that comes here, which you are aware of electromagnetic spectrum. And we could use certain element or semiconductors for absorbing the light, because only the semiconductors with the energy band gap which is in the range of the quantum energy of the visible light, which can convert sunlight into the electrical energy. Okay, so that means I have listed a few, but because of the technical reason or feasibility, some of the things are still in working, still in laboratory condition. But at present, silicon is used, and wherein again it is a amorphous silicon people are using, and that is what the importance of energy band gap. So that is what the intention of learning energy band gap, or to identify the material, suitable material for solar panels or photovoltaic cell. Okay, now let us see the conventional current flow in the case of intrinsic semiconductor. Similarly, we had it for metals. Okay, in the metals we had just free electrons. Now we are having electrons as well as the holes. So these blue ones are the electrons, and these gray ones are the holes. Okay, so that means this is a battery that we have, and we are having the current flow like this. Okay, so in the clockwise direction. So now if you consider the electrons, you know that electrons travel in the direction opposite to the applied electric field. So this is the flow of electrons, and in the case of holes it is in the opposite direction. So that means in the case of holes, the flow of hole or movement of hole is in the direction of the applied electric field. That's all you need to learn. So this is what the conventional current in the case of intrinsic. To understand better, you should refer back the similar picture which I had shown for the metal. Here let us learn, or just know, where the Fermi level is present in the case of intrinsic semiconductors. Okay, we know that this is valence band and this is conduction band, and in between, if the gap is there, it is energy band gap, which we represent as Eg. Okay, fine. So in intrinsic semiconductor, when an electron gets enough energy, maybe by thermal or electromagnetic radiations, it can be excited to conduction band and leave behind a hole in the valence band. Okay, so holes could be present here, and electrons could be present here. So this is what we call as a electron hole pair. So hence number of holes in the valence band will be equal to number of electrons in the conduction band. That is, the probability of occupation of energy levels in the conduction band by the electrons is equal to the probability of occupation of energy levels by the holes in the valence band. Further, if or as the excitation and de-excitation process continues, the conduction electrons are distributed between the top part of the valence band, okay, top part of the valence band and bottom part of the conduction band. Okay, and hence the average energy of conduction electrons will be 0.5 Eg. So that means the average will be 0.5 eV. So that is what this level is identified. Okay, so where it is, so that means this is Fermi level for the intrinsic semiconductors lies in the middle of the forbidden energy band gap. Okay, so this is where we are having the Fermi level. Okay, so that is what the understanding. So that means the slides gives you the information about the Fermi level in the intrinsic semiconductors. Now let us see the relation between EF, EC and EV in the energy band diagram, which is shown in the previous slide. I am showing it in a very small size. Okay, let us start. In the intrinsic semiconductor, which lies in the middle of the forbidden band gap, that means Ne is equal to NH is equal to Ni, and that is the number concentration of electron is equal to number concentration of holes, and that we just represent as Ni represents number concentration in the intrinsic semiconductors, intrinsic carriers. Okay, and then we have an equation for the hole concentration in the valence band as given by this equation, that is NH is equal to NV into e to the power minus of EF minus EV divided by KT. That let it be equation 2, where NV is the effective density of states. Similarly, if we consider the electron concentration in the conduction band, then we have this equation, that is Ne is equal to Nc into e to the power minus of Ec minus Ef divided by Kt, wherein Nc is the effective density of states in the conduction band. Now you observe this equation 3, wherein the number of electrons in the conduction band, which depends on the effective density of states, that is nothing but Nc. Okay, effective density of state, and the distance between the Fermi level from the conduction band here. Okay, so that means this is the distance, right? Ec and Ef, that you could view here, Ec and Ef. Okay, that is nothing but the distance of Fermi level from the conduction band. Similarly, if you just remember the equation 2, again number of holes in the valence band depends on the effective density of states in the valence band and the distance between the Fermi level from the valence band. So that means where there we have the distance between EV and EF. Mathematically, if we work out, then from equation 1, 2 and 3, you could get the expression for EF, which is what I told to get the intention. EF is equal to EC plus EV by 2. So that is what we have. So EC plus EV by 2. So that means where it is lying? It is lying at exactly half of the forbidden energy band gap.